In previous videos, I've mentioned that in an electric circuit, the electric field lines will go around corners and follow the shape of the wires, but I didn't allude to how that worked. Here we're going to go ahead and explore the mechanism by which that happens. So at the moment I've got a fully charged capacitor here, and I've drawn in the electric field. So remember, inside the capacitor, you have a nearly uniform field with all the field lines running from positive to negative, and the strength is quite high. Outside, there's a much weaker field, which is why I'm drawing fewer lines outside, called the fringe field. So let's imagine hooking up some wires to my plates. And at the moment, I don't want to connect the wires together. We'll get to that. But at the moment, I just want to look at a couple of wires just like so. All right. So it turns out here, when I attach the wires, let's just think about what happens to an electron, say, sitting right here. If I'm an electron sitting right here, and I'm seeing a electric field line pointing to the right, which way am I going to be feeling an electric force? Yeah, you'll be feeling it to the left because remember, negative charges feel the force in the opposite direction of the field. So that means that this electron here is going to feel an electric force pulling it to the left, like so. And that means it's going to start moving to the left. Now, when it gets to the edge of the wire, where's it going to go next? Well, it can't go anywhere. So what winds up happening is you actually start building up a bit of negative charge around this corner here. All right, let's repeat this over at, say, this corner here. So over at this corner here, again, it'll be the same deal. The electrons there will be feeling an electric force pulling it to the left. So that's going to leave behind partially shielded nuclei in the material to leave behind a positive surface charge on the wire like that. And this sort of process occurs all through the wire. As the electric field lines are passing through the wire, it will drag surface charges around. And although it's a little tedious to show, you can eventually work out that you have, in this case here, where things are disconnected, you have a fairly constant charge distribution along the, let's do a little better job there. You have a fairly constant charge distribution along the length of the wire like so, and then the same kind of deal over here. So that's if we just plain have our disconnection. So we'll pick up a surface charge all the way along, but what these surface charges are doing is they are adding electric fields in to the external field. And so in this case here, where we have disconnected wires, the net result will be of the surface charges here is that we will be left with no net electric field inside the conductor. So just what we've had before, it's a conductor in equilibrium. The net field is 0 inside for this disconnected case. Well, now let's go ahead and revisit or think about what will happen if I now hook up a wire to my capacitor, so no gap. So again, same deal. We will have positive charges here Negative charge is there. We'll be running the electric field lines at a high density between the plates, and we will have a weak fringe field outside the plate. Here, let me just finish that off so we see that the line does indeed close around. Okay, coming off the positive plate. These are heading out basically straight. And then once again, we look at this. And now the deal is that we are going to actually attach a wire. And as again, an important safety first thing, this wire should have some resistance to it. Otherwise, things could get very hot. So I am going to specify that this is a high resistance wire. I'm also going to specify don't actually build this yourself unless you've had appropriate training and supervision. So this is high resistance wire. Again, safety first. So now what's going to happen? Well, here we're going to need to be moving charges along. And so this means that we need to have a net electric field inside. So again, surface charges will move around because of the influence of the electric field. But because this is a high resistance wire, we've seen that we need to have an electric field within the wire to shove the charges against the resistance that's being provided from the collisions with the shielded nuclei. So the net result is going to be that we need the electric field line, which I'll draw in purple here, after we've connected this, to follow along the wire. In fact, there will be a whole collection of lines, but I'm just going to draw one so that it doesn't get cluttered. So it's going to be the same kind of deal. These electric field lines coming out from the fringe field will have had the effect of shoving charges around to get stopped on the surface, and then those surface charges will interfere with the fringe field. Now, the difference is the density of the surface charges. So near the plates of our capacitor, the density will actually be quite high. And then as we go along, the density will drop off, and then same deal going the other way around. There. So it'll look something like this for a surface charge. Whoa, did not want to lose that. It'll look something like this for a surface charge density. So how does that help us to get an electric field everywhere? Let's look at a few different slices of this. So the first set of slices I want to look at is, say, let's look at a slice of the wire here and a slice of the wire here. So if in this region, I need the electric field to be pointing down in here. So let's just follow that through. So here we're going to have a stronger electric charge. Here we'll have a weaker positive electric charge. So what we get from this region, we will have a fairly strong electric field running both ways. So let me actually change the color of these lower ones here, just so we can think about it a little better. They will be giving contributions that look, say, like this. Oops. And like this. So it looks just like the bit up here, but weaker. So if I add up the contributions, we will have the contribution to the electric field from the ring above and the contribution from the ring below to give me my net electric field pointing down. I will leave this, so let's go ahead and repeat this for the negatives over here to the left. So here again, I'll mark these, so negative, negative, negative. Now here, it's going to be the same deal, except the directions are reversed. Like that. And then for our our weaker contribution down here, again, it's going to be the same kind of deal, heading inward, but weaker. So then again, right here, the contribution from above will be pointing upward. And the contribution from below will be pointing downward, but weaker, to give me a net electric field pointing up, which is what we should have right here. Then finally, maybe the one other point to look at would be right in here. Let's look at these. So here where we've got a pair of rather weak positive charges, in this region here, the electric field lines from this will be heading outward everywhere. And here, they will be heading inward. So again, right here, the contribution from the charges coming from the right, we'll say E plus here, is pointed to the left. And similarly, E minus from the negative charges is also pointing to the left. So then I will have a net electric field pointing to the left. And in fact, the electric field, even though I didn't draw it this way, the electric field everywhere will be roughly constant. So that's how the charges know how to go around a corner. Alrighty, so in the next video, we'll be taking a look at how to measure voltage and current. And we'll catch you there. Have a good one.